My goodness gracious. Record.
I have a question.
Yeah.
For number 4, we're just writing out the equation. Like we're not finding the answer. We're just
Number 4,
doing
where?
12.1, I believe.
All right, 12. Okay. Let me see. How do we get back there? Dadgummit, I went too far. Here we go. Number 4. Yeah, just find the equation. Is that your question?
Yeah, I just wanted to make sure we didn't have to do like find the answer.
Oh, you can't find the answer because they didn't give you enough information. There's 2 unknowns, right?
Okay.
Okay. All right. Anything else, guys? From hopefully more of you gotten into chapter 12 stuff, the correlation stuff. Of course, we have a quiz on that on next Wednesday, I believe, right? The 2nd. And what's the last day of class? I know, by the way, I'm not asking you. No, the last day class is the 7th. I love you guys. Hey guys, what class is this again? Wouldn't that be great? No. It's the 7th, right? Believe me. In fact, yeah, dude. What do you mean that soon? Yes, that soon. So let me show you. You ready? I love you guys. What day is the final, guys? I love how
December 9th.
Yeah, the 9th. So why does anybody believe the last day of class is after the 9th? That doesn't make any sense. So again, just to show you, look at this thing I put up here for you. Have you guys ever seen this before? So down here, the review for the final is that Monday. That's the last day. That's why the review for the final is on that day, because it's the last day. And then Wednesday the 9th, from 1:45 to 3:45, we'll all be here and we'll all be on Zoom. You will all have your cameras on and we'll all take it, and it will be not awkward at all. It'll be fantastic. We'll have a great time. I mean, back in the day when we were on campus, I would bring cookies and stuff for the final, but now you'll have to bring your own BYOC. Bring your own cerveza. I mean, your own cookies. Bring your own cocktail. There you go. Yes. Well, why not, man? The final, even if it's not right, it'll be more interesting if you're all drunk. No, I'm not saying get drunk. If you're watching this, Dean. Hey, Dean. Duly noted. Okay. All right. All right, guys. All right. So nothing else about homework? You guys are good?
Just a quick question. Sorry.
Yeah. I just realized.
For number 57, for 57, it's asking to state the dependent and the independent variables for like each of, there's like A, B, C, D, and E.
Sure.
Is there a way to like look at like an example and then just figure out from the wording which is the dependent and the independent variable? Because I definitely get confused when I look at that.
So look at the first one. A study is done to determine if elderly drivers are involved in more motor vehicle fatalities than other drivers. So you got the number of fatalities is one variable, and the age is the other variable. Would it make sense to say, how many fatalities would a 75-year-old be involved in? Or would it make more sense to say, what age is somebody, if there were 80 fatalities, what age is that person or something? I mean, let me see if I can say this better. So independent variable is the input, and dependent variable is the output. So which one would be the input? Which age or fatalities would be the x-axis? Let me see.
It would be age.
Yes, because you would say, how old? You would give me an age, and you want an equation that would spit out a number of fatalities, wouldn't you?
Yeah. Okay.
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 So that's
Thank you.
pretty much how you do each of those. In fact, they kind of tell you, doesn't it? Like part B says, if the weekly grocery bill changes based on the number of family members. So see how it's based on the family members? So grocery bill would be dependent on the number of family members. Therefore, family members are the input, independent, and grocery bill is the output, the dependent. So they word that one even nicer. Is that cool for that section?
Yeah, that makes sense. Thank you.
Okay, you're welcome. How's everybody else? Anybody else? I did have one question. I thank you. I got so wrapped up in calculating all the grades that I haven't put somewhere for people to turn in chapter 12 work yet. So I will obviously include that. Let me see. I thought maybe I have. Oh, I did. But are they not in the modules? Is that the problem? Oh, I didn't put a module for it yet. Okay. Understood. All right. Let's see. Turn in chapter 12. Homework here. Shit. How's everybody else? Oh, come on. What are you doing? There you go. I love technology. All right. How's everybody else? Anybody else? There we go. It should be up there now. So let me know if you can't see it. I think I need to add another section in there, but oh. Everybody else good? Anybody else? Any questions, homework, anything? I will have I don't think anybody asked about this, but I will have a practice final. Did anybody ask about that? So I'll be posting a practice final probably after Thanksgiving. I don't know, unless somebody wants it sooner and you email me. And then of course I'll have a solutions video for that. And that'll be one thing we can go over on the review day, will be the practice final. All right. So everybody good before we get back into where we left off? Okay, let's see. Where did we leave off? What class is this again? I'm joking. Let me see. So I think we finished chapter 12, but I don't know. Do you guys want to do another example? Anybody need another example from chapter 12 stuff?
Yes, please.
Okay. So this is pretty much all in the calculator. So here we go. Let's do this just because. Let's see. Does that look all right? Let me see. I'm looking at it. Hold on. Yeah, maybe. All right, let's try it out. Let's see what happens. So I'm looking at number 74. Right here. All right, so if you want to play along, go ahead and throw this into L1 and throw this into L2. Oh, I might as well do it too. Let me wake up my calculator. Bam, bam, bam. So number 74, coffee consumption and death from heart disease. Oh my God, Jeff. I drink coffee every morning. What am I doing this problem for? Well, all right. Let's see. Chip, chip. All right. Interesting. Oh, this is nice. This seems to say that as the coffee consumption goes up, the deaths go down. It's intriguing. So I feel better about drinking my coffee. Have you guys got all that data in the calculator yet?
I have.
Thanks, Janik. Go ahead and try to take it out as far as you can. See if you can get the line of best fit. See if you can get the data to show up along with the line of best fit on the calculator. I like that reaction, Heidi. Really? Really? You want me to do work? Yes. All right, let me see. Obviously, if you have the book, you can look this up in there, right? Oh. I'm not sure what that means. Is that like hieroglyphics? What is that? Oh, oh my God. Today is just, that just goes along with today so well. Oh, wait a minute. So Alexis has her bird. You've got your bird too. How many people have a pet bird?
We live in the same house.
Oh, that's so cool. I think you had mentioned, I can't remember now. I can't.
Yeah.
That is intriguing.
Okay.
That is so funny. All right, guys. So let me share my calculator. I'm going to stop sharing this. Oh, shit. Where's my calculator? There it is. Okay. So I got all the data in here. Where do I go to calculate the line of best fit in the R and all that kind of stuff?
Go to stat. Scroll over to calc. And enter 4.
Cool. Did everybody get this? Let's see if did I put them in there right? You never know. Let me know. If it's different, let me know. I could have put something in wrong. Could be
No,
my.
you did it right. I got the same thing.
Well, we could both be wrong, Janik.
That's what I got.
All right. How's everybody else? You guys good?
I got it. I know you showed us a couple of times before, but I always seem to miss it. Could you show us how you store that so that way we don't have to go and type it in when we try to do the stat plot?
How I do what? I'm sorry.
Like when you just store that information.
Oh, to store it in the Y, so the Y equals thing will show up.
Uh-huh.
Is that what you mean? Oh, let me get this back to normal. Let me clear this. So you want to clear the Y equals. So if we go to calc and do the calc, right here was to store regression equation. If you want to do this, it's up to you. You go to vars, Y vars, function Y1, and it's going to store it. Now it'll be stored in Y1. See, there it is. In all of its glory. My God. So many decimal places. Oh my God, Becky, look at her decimal places. So is this a decent correlation? What's your gut tell you? There's a couple of things competing here, but what it up here tells me it probably is okay. What tells me it's a decent correlation?
The R.
The R value.
Yeah. And it's negative, which made sense if you looked at the points. It seemed as the X's went up, the Y's went down. So that's a negative correlation. The thing is, it's a very small sample size, but I know that this is still enough to show evidence of correlation. The smaller the sample size, the more definitive your evidence has to be. You knew that on day one, didn't you? Smaller sample, bad, right? So this is a very small sample size, but this R value is enough to be correlation. So let's see if visually it matches up. So if you have your own calculator, the same one you had when we did this the first time, if you should be all set up. Mine is not for some reason. I think I had to turn mine off for a different class. So you should have your scatter plot turned on, L1, L2, your favorite little symbol selected. What do I hit? If I hit graph now, I get something I get nothing. What did I not do?
Zoom 9.
Zoom 9, exactly. Make sure your 9 is stat, zoom stat. And there you go, it looks good. That kind of matches up. It's decent correlation. It's not fantastic, which is why it's a little bit further away from -1, right? You guys with me? -1 would have meant they all perfectly line up. These do not perfectly, but they're decently close. Do you guys see how this might be a bit of an outlier? Do you see how if I took that point away, it doesn't look like it'd be more like this? The correlation. So there's a chance that this is an outlier. There's also a chance that this is exponential. An exponential fit looks like it would go through pretty well. And all of that is beyond what you have to worry about. You with me? Okay, maybe. That's kind of neat. Whee. All right. So for your homework in section 12.3, I think, in 12 something else, you can just take a snapshot of your graphing calculator, right? When they ask you to do the line of best fit for the final exam and for the quiz, you can take a snapshot of your calculator for this part, because I would normally have you come up to my desk and show me your line of best fit in your scatter plot, but obviously can't do that now. So
Just wait. Do you mean we can just like take a photo of our screen on our phone and then just use that?
and then submit that. Yes.
Okay. Like does the calculator actually have like a screenshot option or no?
No.
Okay. Got it.
They really need to update this. They need a scroll bar and screenshot option. That would be fantastic. How we would graph. What do you mean? Do you mean if you're given, I'd rather you, if you do not have any capability to screenshot, then you could try to copy the graph down that you see, but it's got to be, decent enough copy. Does that make sense? Now, let me make sure I understand. There's somebody asking me, you want me to show you if I give you a line, how to graph it? Is that what you want me to show you? Person who is, you mean like in section 12.1? No. All right, so I'm talking to a few different people. You can draw it, like I said, it just has to be a decent copy, right? Now I'm talking to the other person. So I can say, okay, all right. Section 12.1. Any questions on what we just did? You have to know those steps. You have to just know them. You're gonna have to do it for the quiz and for the final. You have to be able to get to this point and then take a snapshot. Okay. So let me see. Somebody has a question about, I'm going to stop sharing this. I think you're asking, well, let's take a look at the book. Do you have an example from the homework? Five. Okay, let me see. Oh, okay. All right, I'm with you now. So let's see. Maybe we'll share the whiteboard. Why not? Ooh, can you guys see my whiteboard on the computer screen?
Yes.
Yes. Okay. Oh shit! I gotta plug it in.
Well,
Is it connected?
Bluetooth connected.
Oh. All right. Let's see. Oh shit! Of course I'm on the wrong screen. Dad gummit. Hold on, everybody. Let me see if this will work. You can just get up off your ass. Yeah, I'm gonna have to get off my ass. Okay, it won't work. Fine. Let me turn Mars off. Hold on. Mars, you're a good planet. Just, go away for now. Oh my God, Zoom. There you are. Bam. Okay, so I got a really quick request. I know, hold on. If I give you an equation like how do you plot that equation? What do you know from this equation? What do you know?
It has a slope of -2/5.
All right, somebody else tell me something else.
The y-intercept,
Y-intercept is what?
4,
Almost.
+4, or 0.
0, 4. So it's got to be a point, right? Yes, I am one of those teachers. Why? Because that's the correct way to do it. So it's anyway, I know what you meant. But intercepts are points. So you got to name both parts. So how do I plot this line? Using just this. Keep it going. Where do I start? What do I plot first? If I want to plot this line using this information, what do I plot first?
Y-intercept.
Yes, start somewhere. You got to give me a point to start at. And the slope is directions, how to get back to the line. So what's the slope tell me to do?
Go down 2 and over 5.
Yeah, if I go down 2 and over 5, I get back to the line. Gia. There we go. Done.
Sorry, man. Jealous much? Yeah.
Dude, I just do down. Oh, it looks really far off. To me, it looks fine. On the screen, it looks wrong. There we go. Let me see how that looks. Still looks wrong. God, it's so weird. So up there. So down 2 over 5. All right. Is that all right? Are you guys okay? I mean, does that make sense, everybody?
Yeah.
I know for some people it might have been a long time since they did this, but that's the slope and the y-intercept. That's what they mean. Okay, I like it. All right, anything else from homework stuff?
I have a question.
Yes.
On 12.2, number 60, they give us, it looks like 3 variables. Or am I
Oh
confused?
yeah. Okay. Some of these are a little confusing. I agree. Number 60.
Yes.
Is that what you said?
Yeah,
All right, let me
60.
Do. Yeah. All right. The year is extraneous. The year is. They shouldn't have put the year. They put the year just to tell you that's the year they were in. The data is poverty rate versus cell usage.
So the year, do you even want it on the graph? Like, do you
The
want it
year
on
is
the
not on the
point?
graph. No. The year is not showing up at all. They just put it there for information, just to go, oh, this is interesting. But look here, poverty rates cell phone usage. Those are the important data points. I like it. So they obviously want to see how do the poverty rates and the cell usage, are they related somehow? This is a remarkably small sample. So, yeah. Oh, this is just making a scatter plot. All right. That's nice. Yeah, so this won't show up on your plot at all, right? That's kind of sucky. It's sort of like this. Look here. Like this is not going to show up on your plot at all either, but that's a little easier because it's not even numerical, right? So it's sort of like the years here are just labels, and this is the data. The schools here are just labels, and this is the data. Yeah, same idea. I like it. Good question. How's everybody else? Everybody good? I feel like I'm all up in your business. Let me step back here.
So for the questions you just showed, would you want us to just plug it into the calculator, or do you want us to like make our own scatter plot?
Yeah, in section 12.2, make your own scatter plot by hand. Ha, 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 ha. But for the sections where they ask you to figure out the regression equation and the correlation coefficient, then you can do it with your calculator.
Okay.
Yep. Anybody else? Okay. I think there's only, yeah, there's only 2 of those that you have to make your own scatter plot for. Yeah, yeah. So that'll be fine, you guys. That's easy. Okay, okay. So let's get back. Let me think. Maybe I need you. Yeah, I do. Come here. So we're done with chapter 12. Right, unless anybody has any questions. So we're going to come back to chapter 11. And the main reason I skipped chapter 11 was to give us a bit of a break. So now our break is over. So chapter 12 was sort of like our easy chapter. So hopefully you agree with me. It's relatively easy. Chapter 11, we get our last new chart. So we got the z-score chart, we got the t-score chart, and now we're getting a third chart today, right? Okay, and I know you're all out there going, there's got to be another chart. Come on, Jeff. There is. This is the last one. And this one is neat. This one's called the chi-square distribution. And you're like, what? This is not related to Dragon Ball at all. It's not like Dragon Ball Kai. Sorry. No. Although I do teach graphing inequalities like with Kamehameha, but that's about, so just showing you how big of a geek I am. Chi-square. So this is the Greek letter chi. The square is a part of the symbol. This is one symbol. So we're not going to be square rooting chi stuff. Okay. What the shit is it? So here's what you ready? Ready? This is very neat. I'm gonna kind of like attack it and then step back and then attack it again. So just watch. What is a z-score distribution? Like if it's a normal, let's say a standard normal, right? Then it looks like this, doesn't it? Weehaw. Stay with me, stay with me. Now, what creates this distribution? Well, there's this formula that I think I showed you, but that's not what I'm talking about. What would I actually be plotting here would be z-scores for data points. So I would calculate a z-score from a data point, and then I could plot it here. You guys with me? Isn't that one way I could construct this? And this is one formula that I could use to construct this picture from. Is there another formula that would construct this picture? Yeah. What about this guy? Isn't that a different formula that if NP and NQ are greater than equal to 5, then it would construct this picture? Wouldn't it also construct that picture? Yeah, I love it. So this picture exists by itself, but there are several different formulas that lead to the creation of this picture. And any z-score I calculate would fall somewhere in this picture. All right, let me stop for a minute. So I like to describe chi-square in terms of the formula that creates it, that the formula that's step by step. What do I mean by that? This formula does not describe the whole shape. This formula is individual things that fill in this shape, right? Stay with me, stay with me. Okay, so I'm going to erase the bottom part of this stuff. This is all old news mostly. So here is what chi-square is for. Let me explain why the shit do we have a different distribution. So coming back to this, what controls the shape of this? Why is some of them really skinny, some of them okay, and some of them really, wow? What controls the shape?
The data.
In what way? So like the mean could be the same for all of them. Maybe they all have the same exact mean.
Standard
What is
deviation.
Yes, sigma, standard deviation. Stay with me, stay with me, stay with me. So this picture, the shape of it is controlled by the standard deviation. And then it tells me how things are distributed in that shape. Are you guys with me? So what if I wanted to investigate standard deviations? What if instead of having a known mean and then taking a sample and seeing where it falls in this, what if I have the other way around? What if I have a standard deviation known and I wanted to have all the sample standard deviations distributed? What would they look like? All right. So the shape that governs how normally distributed data points exist, how they flow, is controlled by standard deviation. What if the standard deviation itself is what I'm investigating? What kind of distribution would it live in? It obviously would not live in something like this because this guy's shape is controlled by a standard deviation. Does any of this make any kind of sense? Not at all. Okay, some of you guys are looking at me like, try again, buddy. All right. Shit. So again, if I know the standard deviation, I know how skinny or fat a distribution of data points is. What if my data points are standard deviations? Are the data points. I would put all my money on the shape of that thing, plotting all the standard deviations. I'll put all my money on the shape not being the same as this. Because this guy's shape is controlled by a standard deviation. So what does the shape look like? Well, first off, here is the most, so just like we have, this is what you would call like the most basic z-score formula, correct? This is the first one we learned. It's how we kind of built off all the other ones. Are you guys kind of with me? This is what I would call the most basic z-score formula. So the most basic chi-square formula Oh, thank God I remembered. I just like, I haven't looked at this in a long time. Is this guy. This is the most basic chi-square formula. I want you to notice something. So look up here. Isn't there a known mean? And then I have a data point, right? Because doesn't the z-score tell you the number of standard deviations from the mean to the data point? I mean, blah, blah, blah. So this is a comparison between a known mean and a known data point. Well, look here. This is a comparison between a sample standard deviation and the population standard deviation. So you ready for this? You're all like, just keep going, dude. We're not ready for any of this shit. I understand. If you plot this, it will most likely look something roughly like this. This is something I affectionately call the Jabba the Hutt graph. Oh. If you've ever seen Star Wars, you see why he's got a big old tongue out there. Poor little Jabba. All right, Jabba, go away. Oh. What's another way to describe this? This is skewed to the
Left.
I love it. So this is a skewed left distribution. I want you to realize something. What is the smallest S can be? What's the smallest standard deviation that some data could have? Think about it. What does standard deviation mean? It means how far the data points are on average from the middle. Well, what's the smallest that distance can be?
0?
Zero. Yeah, that would be data. Like if I had, this is my data set, 1, 1, 1, 1, 1, 1, 1, 1. What's the standard deviation of this? 0. So see, this is a hard stop. Whereas this guy goes forever in both directions. This guy has a hard stop. And then most standard deviations are in here, and then some get really, really big. So if I take a sample, isn't it possible that I could take a sample of people's ages and get this kind of a sample? So the standard deviation would be kind of huge, right? So it's not likely, but it's not impossible that I'm going to get a very large standard deviation from a sample. Most of them should be down here. So this kind of sucks a little bit. What kind of sucks? What's so beautiful about this distribution? It's symmetric. What else is beautiful about this distribution? I can have, since it's symmetric, -1 to 1 means something and so forth, right? This is not symmetric. It's not centered around 0. All right. I love you guys. Right now, please stay with me. You're all like, what does this mean for me, Jeff? What is my homework going to look like? Huh? What is going on? Do I have to watch Star Wars to do this? Oh, no, you don't. All right. Especially not the prequels, kids. If you haven't watched the prequels, just don't. Okay. Sorry. Maybe you should, just so you can see what shit they are. The third one's not as much shit, but it's still shit. All right. So let's see. Let's get closer to what we're going to have to worry about. Help me out, guys, real quick. Here's a z-score, right? Can somebody square that for me? Say it louder.
2.706.
706. I like it. Okay. What about 1.96? What do you get when you square that?
3.842.
I like it. All right, just keep that in mind. So, let me see. Do I want to? I'm just gonna leave that there for a minute. You're like, what the shit's that mean? So here's what this means. For a sample of size 2, let me make sure this is right. I can't remember now. I think it's a sample size 2. Then the degrees of freedom would be 1, correct? The
Yes.
chi-square distribution for degrees of freedom of 1 is, you're going to freak out. And again, we're nowhere near yet what you're going to have to worry about. This is still explaining shit step, okay? So this is way up here. You're going to have to worry about down here. We're not there yet. If I took this thing and I fold it on itself, oh man, this is too awesome. Meaning, let me see. So 1.645 is the one that's got, you can do it, Jeff. What is that? 5% out here. So if I folded this on itself, I would add these two areas together and I would square 1.645. So now keep that in mind. Let me show you this chart. This doesn't, now this is above and beyond what we have to do, but I want you to realize one reason we call this chi-square. Oh, this is so weird. I know, just stay with me. For degrees of freedom equal to 1, this equals a z distribution squared. Let me show you. The minute you get degrees of freedom above 1, it doesn't. But for degrees of freedom of 1, this is true. Stay with me. Now you see why I didn't want to do this immediately after hypothesis testing. You all would have rebelled and said, we're out of here. All right. You might do that still anyway. So let me show you this. Let me see. Did I put it up in here? Yes. Just to show you where this is. If you go to Canvas, down here to unit 11, chi-square chart. Chi-square chart. Oh, so beautiful. What the shit? So stay with me. This is so cool. If you can get this, let me come back to this in a second. If I fold this on itself, that's 5 and 5, that's 10% up, right? 10% to the right should correlate to 1.645 squared for degrees of freedom of 1. Is this related to your homework? No, it's just me showing you something. Stay with me. Oh God, this is so weird. I know, hold on. So watch this. One thing that really sucks about this is this does say area to the right. That sucks because your z-score chart is all about area to the left, right? That kind of sucks. So if I want 10% to the right, which is the 1.645, and remember what was 1.645 squared? 2.70, look right there, 2.706, right there, 2.706. Where's 3.84? I guess they rounded differently. Oh yeah, because it's not exactly 196, but anyway, there's 3.841 right there. That's related to a 1.96 and so forth. Is this really, really important to fully grasp to be able to do your homework? No, the book says nothing about this. I just really wanted to make sense. Why does this chi have a square on it? Because it's related in a very fundamental way to the square of the z-score distribution. You kind of fold it on itself. That's why the symbol has a square on it. You're like, man, that's a long way to go to explain that shit. Just say it's got a square on it, Jeff. All right, I know. All right, now, what kind of problems are we going to use this for? Well, the very first kind of problem we're going to use this for is something really cool called the goodness of fit test. That's going to kick so much ass. Okay, so let me stop for just a minute. Let me let you guys mentally catch up. The first thing I really want to do before we get into the specifics of what a goodness of fit test is, I want to make sure you can read this chart correctly. In fact, maybe I want to, Okay, let's do this. Is everybody, are you guys all able to access Canvas? Can you look this up, this chi-square chart? You got that, everybody?
Yeah.
Yeah. Okay, so let me go back up here. Share. I got so much crap over here. Okay. All right, light, don't fall over. Okay, good. So let me show you something. One thing we could use this for is to make confidence intervals for standard deviation. So what are confidence intervals for means? We get a sample mean, and then we add so much up and down to make an interval within which we're such and so confident the real mean is. Remember that stuff? So it's sort of like a better way than just saying, I think the mean is 7. Well, if you say, I think the mean is between 6 and 8, well, that tells me more. That tells me how sure you are that it's around 7 versus somewhere between 2 and 12. That would be like, holy shit, so you don't know. All right. Is everybody with me? Remember? So I can do this. If I want to make a 90% confidence interval, what percentage is up here?
10.
No. What percentage is outside?
0.05.
Yes, so it's 0.05 on both sides. I love it. So that much we keep the same. The problem is, I want you to see, confidence intervals with z-scores were so nice because if I knew one was negative 196, the other one had to be positive 196 because of symmetry. Do we have symmetry in Java the Hutt graph?
No.
No, we don't. Stupid Java and your tail, whatever, right? So now watch. Can you, and let's say this, the one thing I haven't told you you need is, let's say the degrees of freedom are 8. So let's look at that chart together, right? So everybody got that copy down?
Yeah.
Yeah, draw the Java, draw. So I want a 90% confidence interval. So what I'm doing is I would take a sample and then I would build a confidence level for where sigma falls, right? Same thing we do with confidence intervals for means. Part of that is going to be looking up sort of like the z-scores. I have to look at the chi-square scores that would tell me how far away I am. All right, now stay with me, stay with me. So let's look at the chart again. Where'd you go, chart? There you are. All right, so to find this guy, here's what's nice in the chart. It's on this side. See that? So it's 5%. Stop at degrees of freedom of 8. So I get 15.507. Do you guys see that? 15.507. And then down here, I might as well just show you this kind of problem. Why not? Where'd it go? Okay. And then down here, I want, what's going to be down here then? What's to the right? So this whole chart's about to the right. So if that's 5%, what's to the right of this guy is 95%. Does that make sense? This whole chart is based on to the right. So if I want this chi-square, I got to figure out what's the percentage this way. And if that's 5%, that must be 95%. So if you look at 0.95, I know I'm going to put the board down tiny. I'm sorry. If you look at 0.95 right here, and notice this also. Do you see how 0.05 is here? And here's the middle. And 0.95 is the same distance.
Mm.
All right, it's always going to happen, right? For confidence intervals. So then I want to stop at 8 and I get 2.733 right there. Okay, maybe. So if the confidence would have stayed the same, but the degrees of freedom would have changed, I would have just looked at this same column and this same column up and down, go to the right degrees of freedom. Not a big deal. Okay, maybe. So let me make this and come back to the board. So let me go ahead. This is not the first kind of test, but I think it might make more sense. Well, let's find out what happens. Let's find out what happens. So remember the chi-square formula, the basic one was this. So now watch this. This is kind of neat. In fact, I want you guys, do you remember, just go with me. Do you remember how we created the confidence interval formula? Remember this bad boy down here? Jeff. It's basically the same column. All right. This bad boy. Do you remember where the hell that guy came from? He came from this. He came from this, from which we solved for x, didn't we? Remember doing this shit? Jeff, you could do it. Can you do it? Yeah, there you go. Which then we got here. I don't know if you guys remember that at all. So that's the very first thing. We solved for x and got this thing. And then we said, oh, if I don't know mu, I've got to take a sample, in which case I've got to change the standard deviation. And that's where that formula came from. So now watch. Watch. Isn't chi-square basically performing the same function as z now? Just instead of means and data values, I've got a standard deviation and sample standard deviations, right? So let me solve for sigma the same way I solved this guy for x. Let me solve for sigma. All right, now watch. This is where things get really kind of cool. So if you do this visually, it's a lot easier. So what if I took a sample? What if I took a sample? What did I say? So what was my n in this case? What was my n? If my degrees of freedom was 8. My-
9.
9. So what does this side lead me to? And again, I want you to really understand the formula. Why is this formula so easy? Because both of my z-scores are the same number. Maybe they're both 1.96. One's positive, one's negative. So what's harder here is these chi-squares are totally not related because it's not symmetric. It's not centered at 0. But I'm fundamentally doing the same kind of math. So what do I get for this chi-square? If I use this formula, I get this chi-square leads me to n minus 1 is 8 times, oh, that's what else I got to give you. Let's say my S I get is, so I got to tell you what S we got. Just like here, I'd have to tell you what the sample mean was, right? So say the S I got from my sample of 9 things, let's say I got a standard deviation of 14.2. So this would be n minus 1 is 8. S is 14.2 divided by my chi-square, which is 2.733. So my variance on this side, what do you get when you plug all that stuff in? Let's see.
$215.967.
No?
Sure. For sure.
590.24.
Yeah, 590.24, sure. And then when you take a square root of that, I get 24.4 0.295 roughly. So that's one end. And if I do the same thing for this guy, this will be 8 times 14.2 squared divided by 15.507. If I do that, I get 104.03 roughly. And if I take the square root of that, I get 10.199, which I'll just say 10.2. So then that means that my confidence interval, so my sample standard deviation was 14.2. And then I would say I am 90% confident that the interval 10.2 to 24.295 contains the real population standard deviation. And do you notice that that is not the middle of this? Remember, the nice thing with this was the sample mean was always right in the middle because it's symmetric. This is not symmetric. This is not right in the middle, is it? Okay, then we wouldn't expect it to be because this is not symmetric. All right, that's some exceptionally weird shit, ain't it? There's so much weirdness around this thing that I hope that you guys can see. We're actually doing the same work. It's just I have to do it more spread out because I can't just put plus or minus because my chi-squares are not plus or minus something. They're completely different numbers. So I have to do like half of this completely by itself and the other half completely by itself because these numbers are totally different. Whereas back here, they would have both been 1.96 or something. They would have just been plus or minus. Okay, maybe.
We got a couple of questions in the chat.
Oh, I'm sorry. Oh man, you guys should know better. I can't keep up with chat while I'm up on the board. Let me see. How did you get to 24.295? I just took the square root. I'm just trying to get to the standard deviation, right? Because this is the variance. You with me? So here's the variance, and then I get the standard deviation by taking a square root. Is that cool? Can you repeat the conclusion? Sure. And where did 14.2 come from? Oh, from my brain. I mean, where would X bar come from if I asked you to make a confidence interval? Wouldn't I have to give you this? Wouldn't I have to give it to you? Or at least give you some data so you could put it into the 1-var stats, right? So that's where 14.2 came from as part of the problem. Okay. So here's the conclusion. Man, hold on. We are 90% confident that the interval 10.2 to 24.295 contains the true population standard deviation. So from a sample, we got a sample standard deviation of 14.2. I'm almost certain that's not the real population standard deviation. So this tells me, I think it's between 10.2, 24.295. Right? There's a 10% chance that my interval does not capture it. Why is it such a wide interval? Well, because it's such a small sample size. I mean, it only took 9 things, right? Okay, maybe.
I have a question.
Yes.
So like our confidence, that comes from the fact that on both sides we have 0.05.
Well, the 0.05 came from the fact that I wanted a 90% confidence interval.
Oh, okay, got it.
So they have to tell you what standard deviation they got, what the sample size was, and how confident they want you to be. And then you can do this work to figure out what this confidence interval is. So something that should make a ton of sense is that if I want to find a confidence interval for a standard deviation, I can't use this because this needs the standard deviation in it. Ah, shit. So I need a whole new distribution with its own set of formulas that works for sample standard deviations. Freaky, freaky, freaky. All right, let's do another problem. Here we go. Start fresh here. So let's say we take a sample of, what do you got, Jeff? 21 things. I get a standard deviation of 9.01. And I want to create the 95% confidence interval. For the true standard deviation, for the population standard deviation. Drum a little job of the Hutt. Now I want 95% confidence, which means how much is here? No. I think I heard somebody else say it right. So, 0.25, right? There's 5% total, so there's 2.5% out there. So what percent is to the right of this one?
.975.
Yeah, 0.975. So what are my degrees of freedom?
20.
Yeah, because my sample size is 21. So if you look at the chart, degrees of freedom of 20. Let me pull up the chart again. God, I can't help but block everything. All right, let me see. Where are you, chart? There you are. So degrees of freedom of 20. And I want 0.025 right there, see? 1, 2, and do you see how 1, 2, there's 0.975 equidistant. It's kind of nice. It looks like the picture. I wonder if anybody sees what I mean. So if I go down to 20, I get 9.591. Do you guys see that? So that's this side, this chi-square here. I call this chi-square small because it's the smaller chi-square. What did I say? 9.591? Yes. Now take a second and see if you can see what that one is. So 0.025, go down to degrees of freedom of 20. I get 34.170. And remarkably enough, I call this chi-square big.
What's the equation again?
Oh, all right, here it comes. So for each of these, you've got to apply this equation. So you apply it for this side and you apply it for this side. And it ends up, it's kind of interesting, it ends up being the reverse for the interval you want to make.
Can you say it out loud because I can't see it?
Oh, am I not sharing? Oh, I see, I am sharing, that's the problem. All right. So n minus 1 times s squared divided by chi-square. So for this guy, it'll be n minus 1 is 20. S was 9.01 squared divided by chi-square, which is 9.591. And for this guy, the only difference is the chi-square is 34.170. So when you go to make your interval, they're actually in opposite order here. Oh yeah. Let's see. Let's do this one step at a time. This is the formula for the right side and the left side of the interval for the variance. So on this one, I get 47.515. And for the other one, just plugging this formula in. No, Jeff. I get 169.284. So if I take the square root, I can see what the standard deviation looks to be between. So the square root of this one's going to be 13 point something. 13.011. Oops. And the square root of that one, 6.893. So the standard deviation I got for the sample was 9.01, and we are 95% confident that the interval 6.893 to 13.011 contains the actual population standard deviation. So 9.01 is in there. It's just not in the middle because this is not symmetric. Oh, I'm sorry, I missed that, but you got it. Good. Not sure what that is. Oh, up there. Okay.
Sorry, just one quick question. So when you're going from the, like,
You're muted. Muted, Alex.
sorry, my bird stepped on my keyboard. When you're looking at the 1.167, that decimal, are you square rooting it to get the final answer?
169, this one?
Yeah, sorry, 169.
Yeah, because this is the variance, and I want to know what the real standard deviation is. So I got to square root both of these.
Got it. Okay. Thank you.
And somebody asks, what if 9.01 wasn't there? That's like me saying, can you construct a confidence interval if I don't tell you what this is? No. Of course not. All right, then. So it doesn't make any sense. So of course I have to be given this, or I have to be given a list of data. I could put it into L1 and I can calculate S for myself. The same way you guys had to do it for this, remember? So I have to give you a way to figure out S, or just give it to you. Right, there's no problem otherwise. All right, so let's do this. Let me see here. It's so weird. It's interesting. You're so careful about COVID, and somehow you still get a cold. It's awesome. Hold on, I want to look up one thing. Nope, not there. Here, I like it. All right, yeah. Let's do this real quick. Okay, so let's talk a little bit about that goodness of fit thing I was talking about, and then we'll probably call it a day, because we have a good amount of time to go over this left in the semester, which is neat. Not sure how that happened, but let's enjoy that. All right. So I think you guys will maybe like this a little bit better than this. I'm going to erase all this. Here we go. So first thing, let me see. Yeah, let's start off this one. All right. I can't think of anything else. So let's say we have a bunch of M&Ms. We got some blue ones. So we have a bag of M&Ms, right? What are there? Blue, red, green. Are there still brown M&Ms? I don't have a clue what the hell they are.
Yes.
Brown. What else we got? Red, green, brown.
Yellow.
Orange?
Orange and yellow.
All right, that's enough. And orange. And of course, if you go to the M&M store in New York or somewhere, then you can get more than that. All right. All right. How many categories are there?
Six.
Yes, there are 6 categories. I'm making a big deal out of that for some reason. So tell me this. All right. Riddle me this. If there are, let's make this something not too crazy, Jeff. If there are 66 M&Ms in my bag, right? 66 M&Ms. And I want to see if the colors are uniformly distributed in all M&M bags. Right, so I'm going to test the claim. Oh shit, don't freak out. Don't worry, it's not going to suddenly become a full hypothesis. Test the claim that the colors are uniformly distributed. What would that mean? What would I expect then if that was the case? What would I expect? How many of each would I expect to see? 11 of each. Doesn't that make sense? So I put the expected, right? Stay with me. Nothing major, right? So we crack open this bag. We somehow don't eat any. We pour them out. We separate them into colors. I remember doing that when I was a little kid. We separate them up in the colors, and then we're going to chow down. But right before we chow down, we count how many are actually in each category. But this is what I expect if this claim is true. And so here's what I actually see. So again, this is all information they have to tell you in the problem. So let's say I see 8 of these, and I see, what do you got, Jeff? Oh shit, this is going to be exciting. 13 of those, 12 of those, 7 of those. Let's say I get exactly 11 there, and let's see what's left over here. Ready? 1 down, 0, 4 down, 0, 4 up, 15. Okay, let's see if does that work out? 4, 50, 60. Yes, sorry, sweet. So everybody with me? These obviously have to add up to be 66. So this is what I observe. So I put an O there, and this is what I expected. All right, now stay with. When would I be able to just stop and say, I don't need to go any further? That's not going to be evidence that it isn't uniform. What would have to happen? Every single one of these would have to be 11, right? If I got 11, 11, 11, 11, 11, 11, is that evidence that it isn't uniformly distributed? I really want you guys to get this. Could this be evidence that it's not uniform? Could it be?
Yes.
Yes. Why? Because they're all different except this guy, right? So it's the same idea as before. Is it different enough? Because it's just one bag, right? It's just one bag from all the millions of bags. All right, stay with me. So I really hope it's kind of obvious that the first step I want to take is to find the difference between these two. And I think I've got these turned around. It's too bad. I think the official, you'll notice it doesn't really matter because we're going to square these. So does it make sense that if what I'm trying to test is how different is my observations from my expectations? So obviously that means I'm going to subtract the two. Is that cool? So 11 minus 8, 11 minus 13, 11 minus 12. And now I'm doing it backwards, aren't I? 8 minus 11. Come on, Jeff. It's not going to matter because we're going to square it here in a minute. Negative 4, 0, 4. And then the next thing we do is we square it. So it should feel vaguely familiar. It's just sort of like finding a standard deviation. So it makes sense this is 0 because it's the one that was exactly what I expected it to be if the claim is right, if it really is uniformly distributed. Stay with me now. If I had been talking about 8,000 M&Ms in each, right? 8,000 each, would 16 have been that big of a difference? Square difference, but still. No, but I'm talking about 11. Is 16 a big difference then? Yes. So what I'm trying to get you to understand is it makes sense the next thing I do is I want to know the relative difference. Let me say this right. The relative difference. So the next thing I do, oh yeah, is to divide the observed expected squared by E to see how relatively different it is. So I'm going to need some help from everybody. Well, actually, maybe not. 9 divided by 11, I think is 0.818181. Double check me on that. If that's true, then I know everything. Haha. What's 9 divided by 11?
Yep, that's right.
Sweet. So that means that 4 divided by 11 is 0.364. Which means 1 divided by 11 is 0.091. Let me know if I'm wrong on any of these. What's that going to be, smarty pants? 1.455? Was that going to be 0? And then, of course, so does all that look okay?
Yeah.
So I really want you to see why this math makes sense. If all of these were 11, then that by itself wouldn't have been proof that it is uniform, but would obviously have been nowhere near enough evidence to say that it isn't. So right now I'm saying, okay, they're different. How different? This different. Then I have to square these for much the same reason we had to square it for the standard deviation idea. And then I want to know how relatively important is this difference? Well, kind of relatively important because it's a 9 difference out of 11. So I divide by the expected to see how relatively, so 16 is kind of a big difference relatively. Now add all these up, and that is another formula for chi-square. Chi-square is the sum of observed minus expected squared divided by expected. Oh, shit and a half. Just like there were multiple formulas for Z, there are multiple formulas for chi-square, and they all follow the same shape, just like Z did. So what do you get when you add all those up?
4.183.
Sounds about right. Now, That is kind of like our Z star. This is just like our Z star because it's calculated based on our observations. Stay with me now. Oh, shit. What time is it? Okay, I don't want to keep us too late. I have a whole handout about this too, so don't freak out. I'm going to put that up on the web probably right after class, and then we'll do some problems next time. Where am I? Okay. So let me tell you this. Let's say I'm using alpha equal to 0.05 right now. And I really, now watch. I've left myself no room. That sucks. But here's the idea. Where would I be on this picture if there had been no difference? If all of these were 11, what would my chi-square have come out to be? Where would I be? If all these were 11, what would this have come out to be?
0.
0. So if I get a chi-square 0, that's obviously not evidence they're different. So what would be evidence they're different? Not only do you have to not be 0, you have to not be 0 enough. In fact, you have to not be 0 so much that how much is out here? In this case, 0.05. All right, here's the next weird thing. What's my degrees of freedom? It's not 65. My degrees of freedom is 5. Because for a goodness of fit test, degrees of freedom equals, I love this, you ready? Degrees of freedom equals K minus 1. I love that they use the letter K. Like they misspelled categories. So however many categories you have, minus 1, that's your degrees of freedom for a goodness of fit test. Can somebody look up what that chi-square is going to be? Degrees of freedom is 5. 0.05 is what you're looking at on the chart. What would that chi-square be?
Eleven 11.071.
Let me show everybody what's happening. That sounds about right. So I got 0.05 right here, right? 0.05. My degrees of freedom is 5. So there's my 11.071. So these goodness of fit tests will always be a one-tailed test. It's always, are you far enough up? So it's always a one-tailed test. Anything in here is close enough to 0 to say there's not evidence to show it's different. You have to get out here to show it's evidence that the whole everything is different. So did we make it? What was it? 11.071? How far did we make it? $4.183, it looks like, right? We only made it 4.183. So have we shown evidence against the claim that they're uniform? No. These weren't different enough to say that all M&M bags are not uniformly distributed.
Can you share your screen?
Oh, I'm sorry. You mean my whiteboard? I always forget.
Yeah, your whiteboard, sorry.
So let me say this again. So 4.183, that's what we got. Was it far enough away? No, we were supposed to get this far away for alpha 0.05. We didn't make it far enough away. So we were close enough to 0 that I can't say it was enough evidence to show that they're actually different, that they're not uniformly distributed. So are they different for this one bag? Yes, except for this guy. Were they different enough for this sample to show that all bags of M&Ms are not uniform? No, it wasn't far enough away. Woo! So let me show you this handout real quick. We're obviously going to do more of this, right? We're going to do more of this. Let me show you this handout, and then we'll call it a day. Let me see if I can't sneak in here somewhere. Oh, where can I put myself? There I am. Okay. I'm just going to cash out right here. Let me see. Where are you? Oh, I don't have this ready. Hold on. Jeff is putting on a clinic of what not to do as a teacher. Donde está? Where are you? Oh, yeah. There it is. All right. Yay. So here's what I'm going to post up on the website here. Let me share this. Oh, shit. Okay. So it's basically the same problem we just did, which I don't mind. That's why I couldn't think of anything but M&Ms, because I was thinking about this. So it's basically almost the same. It's got, oh, I think I got all the same colors. Yay, Jeff, with a little bit of help from my friends. And so I've got the O and the E in correct order here. So why do I expect 7? Because I had 42 total M&Ms, right? 42 total right here, 42 total. So I expect 1/6 of that 7 to be in each category, just the same way we got 11 up here, right? And then you can see I just go through all the steps. I have fewer columns here. You don't need all these columns, thank God, right? Hopefully you guys see you could do L1, L2, L1 minus L2, whole thing squared, right? Bam. So you could do them in your lists. So here's how far we got, and that's how far we were supposed to get. So we have not found evidence to reject the claim that they are uniformly distributed. Woo! I'm not going to be so picky on your language here as long as you can communicate to me what this means. So I will post this up. Oh, yeah, on the other side, there's some correlation practice. I forgot about that. So we can do this if you want for some practice. Maybe this can be like my practice quiz. Why not? There you go. So I got some stuff here about percentage of a state with a bachelor's degree and the median income. Those should obviously be correlated somehow. So I'll do that for you. And then we got this problem. If you want to try it, you can, but we're going to do this problem together next time. It's the other way to have a goodness of fit test. Okay. That's a lot. That was a lot today. And I won't see you again until next Monday. So we'll go over it all again because everybody's going to forget all of it. So we'll go over it all again on a week from today. So I'll post this up on the website right soon, right when class is done. All right, that's enough, man. That is so much. So let me know if you need to hang out. Otherwise, you're free to go and have a good whatever your Thanksgiving look like. Hopefully, it's good.
Thank you.
I might grab pumpkin pie from Albertsons or something.
Thank you.
Guys. Maybe I'll make some pumpkin bread. I'll make some good pumpkin bread. Bye, guys.